introduce the basics of cryptography in CTF challenges. Yeah, cryptography is pretty fun. Oh, okay, it's amazing. Uh, yeah, it's pretty fun. It involves like more math and like knowledge. So like for example, like I don't know, like web exploitation, right? You might need a lot more knowledge about websites. But like cryptography is like more math based. So yeah, it's pretty fun. I'll go ahead and introduce some basic ciphers. Uh, get into an intro of like RSA, and then I will, or and then we can like go over some Pico CTF challenges. So it'll be very fun. Okay. All right. So yeah, first of all, what is crypto, or like what is the base of crypto, right? Um, Essentially, cryptography involves taking some plain text. Let's say you want to like send a message from Alice to Bob, or Alice wants to send a message to Bob. You encode a plain text, uh, and you usually use a key, and you turn this plain text into a ciphertext, so that if an attacker like receives the ciphertext, they can't like decode, or they hopefully can't decode it into plain text. Um, Now, in practice, like a lot of ciphers are very insecure, and we will see this like as I introduce um as I introduce some ciphers. But yeah, in practice, a lot of these ciphers are insecure. And it's usually possible to recover the plain text from the ciphertext without knowing the key. So like if you think about a lock, you can brute force the lock or whatever to unlock it. Similarly, uh, with crypto, you can use like various lock picking strategies or whatever to like get the plain text from the ciphertext. Okay, so let's start out with a basic cipher. Um, this cipher is called a Caesar cipher. Let's say you have some plain text like A. Let's say A is your plain text. Oh, um, in order to encrypt with a Caesar cipher, you essentially just take. Right, let's say you have an. Oh, I'm not even trying to you. Let's say you have some like alphabetic string. In order to encrypt with the Caesar cipher, you choose some number between like 0 and 25, and you call this your key. And you essentially shift each of your letters in your string by like the number given by your key. So for example, A shifted by 2, well, it goes A, B, C. So 2 shift by 2 goes to C. If you want to shift Z by 1, you go Z, and then you wrap back around, so it goes to A. And if you want to shift the quick brown fox jumps over the lazy dog by 7, well, if you calculate, then T will go to A, H will go to O, E will go to L, and like so on. So
Does
this is a
anybody,
pretty basic solution.
does anybody have an idea how somebody could easily decrypt this and why it's bad? Anybody? How do you decrypt it? You're just rotating it, right? So what could somebody do if they wanted to get the quick brown fox back from the AOL thing and they don't know how much it's shifted by? Come on, it's the easiest use code problem ever. Let's go. How do you figure out which one's the right one? Dang,
I guess
nobody.
I guess I should mention to
Do
decrypt, you just
it.
shift in the opposite direction.
Yeah, so
So like, you
Albert
see
was
A,
saying
you shift by
something. Wait,
negative 2.
do
Oh,
it.
chat. Well,
That is
just do
not
it.
what we're
Big
looking for.
brain.
Albert, come on, what's the solution? You know it. How do you
Uh,
decrypt it not knowing the shift? Dang it, Albert died. Okay, well,
Don't
basically,
if you don't know the shift, how can you decrypt it?
yeah,
I guess I'll give you a hint. There are only like 26 possible shifts, right?
If you don't, yeah, just like can't you just brute force over all of the shifts and then like pick the one which makes the most sense?
exactly. There you go. That is what we're looking for. You could basically
Isn't
just
there
brute
like
force it with
letter
letter.
frequencies or something?
Oh yeah, we're gonna talk about that next. But for this one, there's only 26 options, so you could just brute force it straight up. But yeah, letter frequencies are actually pretty useful for decrypting other ciphers.
All right, yes. So essentially, yeah, as Rohan stated, you can just like in order if you want to decrypt like this ciphertext you receive and you don't know the key, well, you can just go ahead and brute force all the possible plaintext. And if you can use like Python or something, if you print all of them out, well, like you can probably guess the plaintext is not like AOL X like not this, blah blah, and like the only logical plain text is like the quick brown fox jumps over the lazy dog at this line. So you can basically deduce that this is the plain text without knowing the key. Okay. Okay. I've never actually learned how to properly pronounce this. I always pronounce it like Vigenere, but I'm just gonna say Vigenere. So a Vigenere cipher is like similar to a Caesar cipher. Basically, you take a word or like some string as a key, and then what you do is you like repeat that key until you get to the length of your plain text, and then you essentially add up each character in the plain text with the corresponding character in the repeated key, and that gives you your ciphertext. So for example, here, attack at dawn, if you have lemon, 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 and you do like a plus l, there's like a table here. If you do a plus l, you get l. So your ciphertext starts with an l, and then like t plus e is like e in the row, and then t in the column is like an x. So you put an x there. And then you keep going. And then to decrypt this, if you know the key, it's basically the same as a Caesar cipher. You just shift in reverse, right? Okay. So decrypting this is like slightly harder because now there are more than 26 options for your key. There are like 26 to the power of however many characters long your character long your key is, but it is still like decryptable even if you don't know the key. So first of all, if the keyword is like English or like it comes from a dictionary of words, you can probably guess the keyword. So like let's say that there are a million English words, or like, let's say you know that the keyword or know or assume that the keyword is English. There are like about a million words, and if your ciphertext is only like 100 characters long, then you can pretty easily brute force all the keywords, or all possible English keywords to like get your plain text. And there's actually a website that does this for you. There are also like more advanced analyses that like can figure out stuff like the length of your key, and stuff like that. But the point is like this is definitely more secure than a Caesar cipher, but it's still like semi insecure.
Why do you guys think it's a problem that your key can't be short? Like, if you need a really, really long key, what does that mean about what you could send to the other person? If it won't work with the short key, then what can you not send? What type of message can you not send? I kind of gave it away. Come on. Nobody? Well, if you can't have a short key, you can't send short messages, right? You can't just say hi, right? Because then your key could only be or only two letters of your key actually matter, right? So essentially you can't send short messages with the Vigenere cipher.
This is another problem, yeah. Okay. Alright, so we've gone over Caesar ciphers and Vigenere ciphers. So let's go over like one last basic cipher. This is a monoalphabetic substitution cipher, and it's also pretty basic and traditional. Basically, you randomly assign each letter in the plaintext to a different letter in the English alphabet, and then you just substitute the character in. So for example, in this plaintext, if we wish to replace letters, according to our like key here, I goes to capital W. So we replace the I with a W, and then like F goes to I, so you replace the F with an I, and so on. Okay. And then yeah, to decrypt, you just substitute in reverse. Okay, so I guess like, I think someone mentioned this earlier, but like, do you guys have any idea of like how we might like decrypt this? It's definitely a lot harder, but are there any ideas of how to decrypt it? I think someone said it.
You could use like the frequencies of different letters. Like since E is the most common letter, you could whichever letter occurs the most is E. Then after that's like T or A or whatever.
Yeah. So I believe ETA. Yeah, nice. I believe like ETA are the most common English letters or something. But yeah, very nice. Basically, like since each letter is basically guaranteed to transform into another letter, we can analyze the frequency of these characters and see, like, say if one character is like super common in a ciphertext, then like it's probably E, and like the second most common character in the ciphertext is probably like a T, and we can like go down from this and making some like educated guesses, we can eventually like figure out the key and figure out the plaintext. And also like another thing, like words like the, right? The is a very common word. So if you see a 3-letter word, or like a 3-letter word in the ciphertext repeated like all over the place, it's probably the. And so knowing that, you now know what like TH and E are, right? And yeah, there's also like pairs of letters. Certain pairs are more common than others, like TH, and so on. And yeah, there are also websites to solve this as well. So yeah, in the end, basically, traditional ciphers are like breakable. So like, unless you're using them for casual purposes, don't use or like, yeah, just traditional ciphers are usually very insecure. Okay, so now that we have gone over those ciphers, let's do a more secure cipher. Okay, so I don't know how many of you have heard of RSA before, but it's basically a well, it's an encryption algorithm that uses very clever properties of like primes and stuff. Okay, so it's like in practice, RSA is like more complicated than this, but like this is like the core understanding of RSA. So like let's say we have a plaintext M, and let's choose some numbers N and E. We're going to call E our public exponent, and we're going to call N our public modulus. And anybody can like look up these numbers online or whatever. Like, you don't have to make N and E private, basically. N and E can be known to whoever. Okay, so if you want to encrypt something, all you do is you take your plaintext and then you raise it to the power of your public exponent, and then you take the modulus, mod N. Yeah, so you just take N to the E and then you mod N. It's that simple. And usually we choose N to be a semi-prime, so like P times Q for some P and Q are prime, and you'll see like why in a sec. Okay.
Anybody have an idea how to decrypt? If you have C, how do you get back M? Some of the math people would know. If you do a lot of math, you might know.
This is where number theory comes in. Yes. So if you have C, if you have E, and if you have N, or sure, yeah, if you have C, E, and N, and you have the prime factorization of N, how might you decrypt this? This is like more math based.
And what, like, something in the power of what is congruent to 1 mod M? There's a very famous mathematician who names a function for it.
Euler.
I mean, you're close. That's a specific case where the exponent's a prime number, but we want a general exponent. So what's the generalization of Fermat's little theorem? Do you know? Nobody knows. Okay, so Fermat's theorem says a to the p. Hey, there you go. Euler totient, indeed. That is what we were looking for. So basically, if you take c to the Euler totient of n, you basically get 1. So we could use that in order to prove this and get back our message.
Yeah. Alright, so this slide's like kind of mathy. But basically, yeah, by Euler's, I did not put parentheses around this. Okay, whatever. By Euler's theorem, if you have some number, or sorry, by Euler's theorem, m, or like whatever to the power of 5n, phi of n, whatever, is congruent to 1 mod n, where phi of n is this function. If you aren't that like experienced in number theory, just take this for granted, I guess. But basically, if we know the prime factorization of n as like p times q, then we can calculate phi of n. And we know that m to the phi of n will always be 1 mod n by Euler's theorem. So what this means is that if we can find some like E and D such that E times D is like 1 more than a multiple of phi of n, then like, well, m to the power of E times D that's like m to the power of e and then to the power of d, right? And m to the e is just c. So plugging that in, we just get c to the power of d is m mod n. And that just comes straight from Euler's theorem. Okay. So the key is, if we know like phi of n, then we can easily find d, because like d is like, if you guys know some math, d is just the modular inverse of e mod phi of n. And so you can use like GCD or whatever to find d quickly. Basically, you can find it quickly. Okay. Now, does anyone know like why is this secure, right? If anyone can know the public exponent e, if anyone knows the public modulus n, and anyone the ciphertext, then why can't you just run this? Like, what part of this is inefficient for someone who just knows n, e, and c, which are all public, by the way?
There's only like one variable that's left that you can't find. Well, maybe 3 if you guys want a hint. Which 3 variables can they not come up with? Maybe in 4. Okay, this hint is kind of bad. But what can they not calculate? If why can't they calculate d? D is the private key, right? So why can't they do that? Okay, what's the property of big primes? You guys have probably heard about this. What's a property about really like semi-prime numbers that are really big? Nobody knows. Come on, math people, you guys should know this. But okay, I think you could give it away, Jeff.
Sure. So basically, the key is that in order to find our decryption key d, we need to know phi of n, and in order to know phi of n, we need to know the prime factorization of n. And this is where the problem comes in, because prime factorizing numbers is like very hard and very inefficient. Like O square root n or whatever. There's probably optimizations, but it's basically O square root n. And if n is like very big, which it usually is, we usually pick n on like the order of 2 to the power of like 2000. Well, you're gonna have a lot of fun trying to find the prime factorization of n with like 2 to the power of 1000 operations. It's basically infeasible for correctly chosen n. Yeah, basically, oh yeah, also we typically choose like e equals 65537. I think it's because it's prime, and so it just ignores some like number theory stuff.
It's also a very special prime. Does anybody know what type of prime it is? You guys already named him before, but this prime is named after somebody famous. Anybody? Nobody? Sad.
Euclid?
No, it's actually a Fermat prime, which is basically means that it's 1 less than a power of 2. What is 65538 power of 2 to the...
It's 2 to the 16 plus 1.
Oh, okay, that makes sense. Oh, 1 more than, yeah, okay, that makes sense.
So, we just choose E as this because it has some special properties, it's whatever. But yeah, typically n is like very large, so it is typically very hard to prime factorize n. There are some like specific n that become easier to prime factorize. So for example, if one of the factors of n is very small, then it is easy to prime factorize, right? You can just brute force it. Another slightly less obvious weakness is like what happens if the prime factors of n are very close to each other? Can anyone think of like why this might be a weakness? If the prime factors of n are very close.
Doesn't that mean you're getting closer to the square root?
Yes, very nice, right? So if it's very close to the square root, then we can also just brute force values near the square root, and then we will eventually find n. Or like find n very quickly. Yes, very nice. Okay. So RSA is generally secure, but just make sure you choose good n and good e, and you'll be fine. Oh yeah, by the way, I don't know if I mentioned this before, but like, yeah, we take m as like a number. So if you want to send a text message, then you can just use like ASCII to encode m as a number and then send it over.
Yeah, another thing to keep in mind for RSA is that it's actually asymmetric encryption, right? So you don't actually have to know the person you're sending it to in order to send it to them. Like for all the other ciphers, like a Caesar cipher, a Vigenere cipher, a monoalphabetic substitution cipher, you basically have to tell your friend what the key is, right? But for RSA cipher, you make your key public, so anybody could message you, but only you can actually see what they message you because only you have the D to take the ciphertext to. So it's kind of cool. It's basically used in literally whenever you visit a website with HTTPS. That's basically what it's using. It's using asymmetric encryption to make sure, like, even though you don't know the website, you can still communicate securely with them because of asymmetric encryption.
All right, nice. I guess we can go ahead and try some Pico CTF bombs. Okay. Oh, I might have to share my entire screen. Okay, whatever. Yeah, I'll go ahead and share my entire screen actually. Just real quick. How do I share my?
Dang, which ones are you doing? Let's see.
It's just not like some of them have files. I believe, yes. Okay. So I guess like let's just go ahead and go over some of the easier cryptography ones. I already solved some of these a while ago. Hopefully I can still solve them. I did pre-download these files. Okay, so the first challenge is called numbers, and I asked the numbers what do they mean. Oh, okay. Zoom stuff is getting in the way. All right, so I already downloaded. The files. So let's go ahead and like open the numbers. Okay, this is the file. All right, I guess this doesn't really have that much to do about what we talked about today, but like, does anyone have an idea of how they might solve this challenge?
What numbers are they all in between? What's very important?
0 and 26.
Hey, very nice.
Might just be like a
so
Caesar
what do you?
Or...
Well, actually, it turns out it's not actually encrypted. If it's just the actual letters in decimal. So,
yeah.
Well, not exactly. But...
Yeah. This turns out to be like PICO, CTF. Or like P is like the 16th letter in the alphabet. I is the 9th letter. Yes, I is the 9th character. C is the 3rd, and so on. Okay. Do I actually want to do this?
What are the brackets for then?
Well,
it's just the flag format.
All the flags are formatted. Wait, let me. I could actually show them live because CyberChef is kind of broken. Hold up, let me.
Oh sure. I should probably learn how to use CyberChef. I was using like cryptic. Okay.
Well, yeah.
I guess like if you want to screen share it.
Yeah, so CyberChef is pretty OP. Wait, could you send me the numbers in the chat?
Oh, okay. Oh boy, time to test typing skills. Okay, I'll just type these out.
So essentially, we can convert it from decimal, right? So we could from decimal, and then we'll add. Where is this? Add. And then we'll add the lowercase a to it. Okay, there we go. And then once we put in the numbers, it should be good. Okay, let's try this. No, wait, okay, let's see.
Oh, it's off by 1, I think.
Oh, I had to do a minus 1. Okay, so I'll just do hex and then 69. Wait, what's the hex for a? Oh, it's 70. 69. Oh, it's lowercase? Okay, I might be trolling. Let's see.
I just see like decimal 97.
Okay, that's probably better. 96. Oh, there we go. Very nice. So essentially, we got Pico CTF, the numbers Mason, and if Jeffrey just puts that in, he'll be good. We can do another one though. So that's fun.
Yes, the flag is just is that right?
Yeah.
Yeah. Basically, if we just change like. If we just use some code or whatever to change these numbers to letters, we get this. That is incorrect. What did I do wrong? Is it?
The numbers. Oh, I think it's all caps, maybe.
Oh, it's all caps. Okay, so it was all
Okay,
caps.
okay.
Okay. So I was just converting numbers to letters. Didn't really have much what you talked about. Okay. Did I download this? Yes, I did. Okay. So this one is table.txt. Let's go ahead and open it. So it gives us this table.
Which cipher is it, guys? Do you guys remember which cipher?
Yes, I showed this table on these slides. I'm not sure if you remember which one, but
This is Caesar cipher.
Not
close.
Because we have a key this time.
Yeah, so okay, it says union encrypted file key in a table. And then this is our key. And then can we solve this? Okay. As a hint, remember, like I talked about adding like letters to letters, right? So basically, if you add this letter to this letter, or maybe it's subtract. I think it's subtract. If you subtract this letter and this letter, this and this, that's how it shows me. But, okay, basically, I can go back to this. The table showed up in this slide, or the Vigenere cipher. I'm not going to try to pronounce that. But basically, you can pretty quickly find out this is just the Vigenere cipher. So, okay. I'm going to show you another website because I don't know how to use Cybershift, but I probably should. Okay, where it is. Okay, so the site Crypty is pretty cool. Basically, if you put in the key and like this stuff, oh, well, there you go, it'll just do it for you. Yeah, this is just near cipher, right? If you want to decode, just decode with the key. Crypto is fun. And does this have a wrapper? It probably does have a wrapper. Okay.
By the way, here's the meeting flag if you guys want it. But other than that, I think we're out of time. So thank you guys for coming. If you guys have any questions, stay behind. But other than that, we are done. So see you guys next week.